Alright, welcome back. We are in uh, line integral of a vector field for the part 2. Previously, we have learned about the line integral of a scalar field. So today is we will learn about line integral of a vector field. Alright, in this subtopic, we explore on vector integral calculus. So since this chapter covers substantial amount of materials, you may need to allocate more study time for this chapter than the previous one. Alright, it will take time and practice to get used to the different integrals. And previously, we have learned on transformation or conversion of integral over a curve C to definite integral. Alright, so now we will learn about almost similar with the line integral in the scalar field, and now we will learn about the line integral of a vector field. So it's almost similar like the previous one, but the notation is a bit different. So as you can see here, the notation for the vector field is we more focusing on the difference between the line integral over a over a scalar field and vector field is the function. For the scalar field, the function is scalar function. For the vector field, it is in vector function. So we know if it's in vector function, it's denoted by the unit vector I, j, and k. Right? So for the line integral of a vector field, so this is the equation of the line integral of the vector field. So the difference is the function in vector function is denoted by this. This is a vector function, right? And we have to convert or transform the integral, the path C here, the curve C here, to A and B. So to the definite integral, so that when we transform or convert the integral, then only we can solve this integral problem. Alright, so what else? So this is we convert in term of, we express the function in term of t here. Alright, and then this is a dot product. So as we know, everything that involve the dot product, we will get the scalar quantity outcome, scalar outcome, right? Okay, so here is a r prime t here is equal to this, or in the scalar function it equal to ds. So it's similar, actually similar as r prime t. Alright, so r prime t is differentiate the dr over dt, then we get dx over dt squared plus dy over dt squared. So this is similar like the previous the scalar field line integral. So we just substitute, plug in inside here, and then we get the we can solve this integral. So the advantage of this vector method is that sorry, is that method in plane 2D and space 3D are very similar in most cases. So we can solve 2D and 3D cases because the method for the line integral is similar. Alright, the important application in this subtopic is in the line integral of a vector field is involved with work done. Alright, work done. So work done is usually equal to Fs. Alright, so in this case we will learn more about the work done for the line integral of a vector field. So we go to the next slide. Alright, the idea or the concept of the line integral of a vector field is very similar to the line integral of a scalar field. So recall that the work done by a variable force Fx in moving particle from limit a to b along the x-axis is expressed by this way. So that means the work done is equal to integration between a and b limit of the function in x direction, right? So let's say we have the block here. We exerted the force on the block with the limit a and b. So the block is moving somewhere here in the x direction. So in a or b direction or in the x direction. So we get the work done equal to F over F times D. Alright, then we have found that the work done by a constant force F in moving an object from a point P to Q, let's say point A, P to Q in space, is equal, W is work done, is F dot D, F times D, where D is a PQ direction displacement vector. That means let's say this here is P and Q. So PQ here is a displacement vector in the direction of PQ. Alright, so it's similar. So how do we get the work done is by this formula here, or we integrate by using this formula. But this is the ordinary work done that we have learned in maybe Math 1 or 2. But now suppose that we have this F in the vector field, this force is in the vector field on R cube. So a force field on R squared could be regarded as a special case where R is equal to 0. That means R here is 0. So this is in 3-dimensional. No, I mean the function when the force field on R squared is a special case when R is equal to 0. That means this statement here, P and Q depends on the X and Y. This means this is R2 is equal to 2-dimensional. But when we are given the function force field, the function here, the PIQ QJ and plus RK is in 3-dimensional 3D in the space, right? So we wish to compute the work done by this force in moving particle along the smooth curve C. That means we are not given any value of limit. So that means we are only given the smooth curve C. So how do we solve this work done or the line integral of a vector field in the if we are only given the curve? How do we solve? We have to transform. We have to transform the function in term of t in order for us to get the limit, the curve limit. So how to transform is this is the concept. The concept is similar like the scalar field previously. So this is a two-dimensional. So this is the three-dimensional, right? So the concept is almost similar. So we have to divide C. C is the curve here. So in this two-dimensional, the pink curve here, the pink line here, we divide it into pi minus 1, pi, let's say I is equal to 5, so pi minus 1 here is 4, so pi here is pi asterisk. So that means we divide the curve into the small curve. So that means with the length of ds here means the smallest displacement by dividing the parameter interval a to b into sub-interval. So that means we have divide. This one is for the two-dimensional, and for the three-dimensional is we can refer to this case. So in this space three-dimensional, so as we can see, we divide the curve. Also we can divide the pi and pi minus 1, but by using the tangent unit vector here. So let's say we have the pi here, and tangent unit is somewhere here, and the function is somewhere here. So choose point. So let's say we choose this point pi. This is any point. Choose this point on the ith subarch corresponding to the parameter value ti. So that means here is also ti here. So we have to express this point in term of t. So how do we express is, if ds is small, ds is intermediate-decimal small, then as the particle move from this point here to this point, so along the curve it proceeds approximately in the direction of t. So that means this particle, so this is our curve, so it proceeds approximately in direction of t, the tangent, right? So this is t, the unit tangent vector, and this is f, let's say, right? So this is what it means by this statement here. Alright, then thus the work done by the force in moving particle from, let's say here is 4 to 5, p4 to p5 is approximately, we can use this formula here. So it's involve the f, the force, and the tangent unit vector together with the ds, right? So we can arrange it this way, and then the total work done in moving particle along C is approximately where t, x, y, and z is the unit tangent vector, and the point x, y, and z is on C. So we can approximately express by the summation of force times the unit tangent times the ds here. So you get the work done. Alright, so in order for us to get the work done along the curve C, we have to get the summation of the arch. Alright, but it's quite difficult for us to calculate one and each one by one. So intuitively we see that this approximation ought to become better as n become larger, because when the n is become larger, we get to do its multiple time. So therefore we define the work done by the force field as the limit of the Riemann sums 11 from the previous equation formula, namely by doing this integration here, w is equal integration along the curve C, f, x, y, z dot, this is the tangent unit here, tangent unit, x, y, and z times ds. ds here is equal to the ds is equal to ds, right? The infinitesimals. So the equation 12 say the work is in the line integral with respect to arc length of the tangential component of the force. Yes, because there is t here is the tangential component or the unit tangent of the force, right? So we go to the next slide. So in this slide, if the curve C is given by the vector equation, so we are given the curve C. So that means when we are given the curve equation, we have to do the parameterize the equation here. So we are using, this is comma, right? So that means we have the x, we express in term of t, y in term of t, z in term of t is equal to xti. This is a unit vector plus yt, j unit vector plus zt, k unit vector. Then we substitute t is the inside here because t is equal r prime t. R prime t is equal dr dt. dr dt is equal to the differentiate the vector equation here in order for us to get the curve in term of t, right? So we can rewrite the equation, we can rewrite it here, and then we cancel this out, we get this equation FRT. So please ensure that the force here you have to express in term of t also in order for you to solve solve this formula, to solve this problem, right? So this is the r prime t, the parameterize that we have learned previously, dot dt. So this integral is often abbreviated as, okay, to make it simpler, so we don't have to remember, we don't have to memorize, but we know how to use this formula. F here is dot dr here and occur in other areas of physics as well. So this is the most common formula that you have to know how to use and evaluate this formula. Alright, so then therefore we make the following definition for the line integral of any continuous vector field. So let F be a continuous vector field. There is a force defined on a smooth curve C given that a vector function of RT A is this is the limit A to B here, alright. Then the line integral of F along C we can express this way. So this formula previously that we have we can express it this way to make you more easier for you to get to solve this problem. So because this limit a and b here, and then you are given the rt, the function, the vector function, and you have to parameterize it, and this is also equal to the first equation, the force dot the unit tangent. So these three formula here is similar to each other. Alright, so when using the definition tree, remember that FRT is just an abbreviation of fxt, yt, and zt. That means you have to express the function, the force of the vector here, the f here, in term of t. Alright, so we evaluate FRT simply by putting x is equal to xt, y is equal to yt, and z is equal to zt in the expression of fxyz. Alright, so notice also that we can formally write dr is equal to r prime t dt. So that means dr dt is equal to r prime t. So that means the differentiate of dr is equivalent to r prime t. Okay. Finally, we note the connection between the line integral of a vector field and the line integral of a scalar field. So that means there is a very similar concept. The idea is almost the same. The difference is only the in the vector field and in the scalar field. So we have to identify which function is in the vector field and which function is in the scalar field. Alright, but the outcomes for both, we get the outcome for both is the scalar quantity, a real number. Alright, so suppose the vector field on R3 is given in the component f equal to piqjrk. So we use definition 13 previously to compute its line integral along the C. So we substitute f component in term of pqr here, and we use the dot product. So when we use the dot product, we multiply pi to x prime t, qj to y prime t, and rk to z prime t here. Alright, so we just plus and plus, and then we solve this we can solve this integration here. So what we get, so therefore we have this formula f dot dr c p dx q dy and r dz, where p, q, and r is this way. So that means the integral of along the curve C for this example, let's say y dx, z dy, and x dz could be expressed as f dot dr, where f, x, y, z we can express is in vector way. So you have to know how to identify. So this one is dx here, so y I here is equal to p actually. Z here is zj, this one is equal to q, so this one is p, q, and r. R here is x dz. So this is the way we express or pqr in this formula. Alright, so to make you more clearer, I will give the link of the video so that you can go through the video and you can get a clear vision about the idea, the concept of the vector field. Alright, so it's almost similar with the line integral of a scalar field, but different in terminology, different in the functions in the fields. Alright, so I will give you the link. So this is the note that you have to take note by doing this line integral of a vector field. You have to know the derivative rule and antiderivative rule. So here is the link, you can go to the video. So in this video it will explain and give you a clearer vision what you have learned previous in the vector field. Alright, so you have to go through this video and gain the clearer view, gain the understanding from the video. Alright, okay, we go to the next slide. Alright, we go to the example number 1. So find the work done by the force. If force is given here, F, X, Y, So this force is in a plane because it's only involve x and y, x and y direction. See, so this is a plane. So in moving particle along the quarter circle, so we know the quarter circle is, okay, so this is from 0 to 2 to pi here, and one whole circle, we know one whole circle is equal to 2 pi. So the quarter circle is here, so it's a pi over 2 for the quarter circle. Alright, so how we solve this problem? First is the step is similar like the line integral of a scalar field. First we have to picture this. So the second step is we have to parameterize. So we identify this is the x here, sin t here is y. So we have this curve. Let's say this is the curve. So we have to do the differential of the curve dx. dt is equal to negative sin t, and dy over dt is equal to cos t. Alright, so after we differentiate this x and y here, so we can get this r prime t. Alright, r prime t is similar to dx is in x. We differentiate in order for us to get the t here, right? So cos t also here. Alright, so we get this formula here, and then we substitute x here in term of this function. So we get x squared, so that means cosine squared t, because we want to make everything in the parameter t. So this is x squared, this is xy here. So we get this equation. Alright, so this is the second step. The third step is we have to plug in into the equation, into this formula. We have to plug in. We get this fr function in the r t in term of t and r prime t dt here. Right. So next, what we need to do is how do we solve this integration if we involve cosine square t and sine t? So how do we get this? Is by using the U substitution technique. I believe that you have learned previously the U substitution technique. So when there is given, so let's say 2, we bring the 2 is side here. So we have to differentiate, we have to integrate this 0 pi 2 cos square t sin t here dt. So we have to substitute cos square t here is equal to u is equal to cos square t. Alright, so maybe you can put it this way, u squared, because it's cos square t. Alright, so the rest is sin t dt is equal to du. So we can solve this problem by u squared here. U squared, when we integrate, we get u to the power of 3. Alright, so over 3, so 2 we put outside previously, and here is 2, so you get 0 over pi over 2. Then we substitute u inside, so we get 2 u is cos 3t. So u is, when u is equal to 3, u is equal to cos 3t over 3. Right, so we get here, we have to substitute in this way. So cos pi over cos cube, let's say cos cube 3. When you substitute t is equal to pi over 2, if you substitute pi over 2 here, what do we get is cos pi over 2 is equal to 0. So we get 0 minus, when we substitute cos 0 is 1, right? So we get 2 over 3. Cos here, when we substitute it into 0, we get 1. So we get negative 2 over 3, right? So this is the answer, right? So I will give you one exercise, more similar question, and you have, we go to the exercise. After this we go to the exercise, right? You have to solve it by yourself. I only give you the final answer. Okay, all right. So this is the exercise that I had been mentioned previously. So please solve this exercise here. So if you given f here is a bit different from the previous example, and but it's moving along the quarter circle, which is the same, similar with the previous example, with the RT here is a radius of 2 cosine t and 2 sine t. Alright, so the radius is 2 here. So please solve this exercise, and then the final answer for this exercise is 8 over 5. Alright, so we go to the next example. Alright, for example number 2 is the question is quite similar to the example number 3. So I'll give you the solution for example number 3, and then you can refer to the example number 3 to solve this example number 2 here. So I will leave this example for you to exercise and for you to practice this line integral of a vector field, so that you get a better understanding while doing the practice. Alright, so okay, we go to the next example and let's move. Alright guys, we go to example number 3 here to find the total work done in a given force F here in space along the curve t equal to 1 to t equal to 2, whereas this one is the limit a to b is given, the limit is given within this curve. X is equal to t squared 1, y is equal to 2t squared, and z equal to t3. So first of all, what you have to do is to so this is given, the parameterize is given, the limit is given, so just plug in inside this force here. So for the total work done is equal to F A B here is 1 to 2, right? So F here is this function here. We substitute in term of